Thank you, Hiro. We are about to start our last session for today, so please come in and take your seats. I'll just leave it a few seconds for everyone to come in. Oops. All right, so if you take your seats, we're going to start. I am pleased to invite you to the last session of today. This session is about... Okay, shh. This session is about raw material requirements for the transition. And of course, this is an extremely important aspect. Without raw materials, we cannot produce any steel, and the raw materials that we will need are likely to change quite a lot with the new technologies that are in the making. So it's my pleasure to present to you my colleague, Dr. Baris Shifci. He's Director Industry Analysis at worldsteel, and he's currently responsible for leading the association's research activities on market fundamentals, business strategies, and future prospects for the industry. So, Baris, the floor is yours.
Thanks so much, Osa. Good afternoon, dear participants. So as Osa explained, this session is about raw materials requirements of steel industry's decarbonisation process. So we would like to identify and discuss some potential raw material issues in terms of availability and cost, issues which can potentially slow down the decarbonisation process of our industry. And also, if we see any ways to mitigate such potential issues, also we'd like to also address the ways to mitigate such potential issues. I have my panelists on the stage already, but before introducing them and starting the panel session, I'd like to kick off with a scene-setting presentation. And in this scene-setting presentation, I wanted to provide a very basic overview. First of all, what's the role of steel industry in humanity's decarbonisation challenge? Secondly, what kind of targets the industry should strive to achieve to meet humanity's climate change goals? What key levers are there for the decarbonisation of our industry? And what kind of uncertainties and risks we are seeing in terms of the or surrounding these key levers, which could slow down these key levers for decarbonisation of our industry. So let me start. And I'll be using several charts from the IEA's excellent study, which was published in 2020, the Iron and Steel Industry Roadmap. And here, this slide presents the energy consumption of steel industry. We all know that steel industry is one of the biggest consumers of energy. It's the second biggest energy consuming industry, which represents about 20% of industrial energy use globally. Coal represents about 75% of the industry's energy requirements, and coal is used mainly in blast furnaces where iron ores are reduced and melt into iron. Steel industry is also one of the biggest users of electricity and natural gas. It represents about 2.5% of global natural gas use, mainly in used in direct reduction of iron ores. It also represents about 5.5% of global electricity consumption, mainly in melting of scrap in electric furnaces. We've heard several panelists and speakers today mentioning the centrality, the central role played by the steel industry. Edwin gave some statistics regarding the revenue, how this revenue is distributed across the value chain, and similarly labor. I think energy consumption is another angle which shows the central role or the enabling role played by the steel industry in the global economy. And with such a massive energy use, which is met mainly by coal, steel industry is unfortunately one of the biggest emitters of greenhouse gases. The direct emissions of the sector account for about 7% of global energy-related greenhouse gas emissions. including the indirect emissions stemming from the electricity consumption of the sector and the combustion of steel of gases. The industry accounts for about 10% of global energy-related greenhouse gas emissions. So obviously, steel industry plays a crucial role in humanity's decarbonization challenge. And what kind of targets should the industry strive to achieve to meet humanity's climate change goals? I again turn to IEA's work, which provides the Sustainable Development Scenario projection roadmap for steel industry. And according to this roadmap, steel industry should reduce its emissions to 50% of its emissions in the year 2019. And this would be in line with the Paris Agreement of keeping global warming below 2 degrees. And to achieve such emissions reductions, the emissions intensity, because there will also be an increase in steel demand, emissions should drop by even a larger amount. It should drop by about 60% from the current level of 1.8, 1.9 tons of carbon dioxide per ton of crude steel produced to around 1.8 tons. And how to achieve such drastic emissions reductions? We see key 3 levers. First one is efficiency gains, not only in steel production, but along the whole value chain, including use of steel. Second is increasing scrap use by making use of growing global scrap availability. And the third one is, of course, development and deployment of breakthrough steelmaking technologies. Now I'll go through each of these 3 key levers, provide some details, and also highlight some key risks and uncertainties surrounding these 3 key decarbonization levers. First is efficiency improvements, starting from the steelmaking side. As World Steel, we see a great potential here. Our step-up program estimates that global steel industry can achieve about 10 to 15% energy efficiency improvements by using the existing technology, only by adopting best practices available. And raw materials play a very important role here because raw materials quality are directly linked to the operational efficiency and hence the emissions from a steelmaking site. And here, for example, investments in higher quality reserves, investments in beneficiation technologies, supply of custom-tailored raw materials, supply of carbon, lean, and hydrogen or biomass containing raw materials are expected to help steel industry achieve higher efficiency levels in the near future. And we are very happy to see that major steel makers are partnering up with major raw material suppliers for the supply of custom-tailored raw materials and also carbon lean raw materials. What about efficiency gains in steel use and adoption of circular economy practices? There is also a great potential here. We expect the steel use to become much more efficient and circular economy practices to be adopted at a rapid pace going forward. But what would be the scale of these gains? And again, the IEA study provides us an interesting estimate. The IEA has 2 steel demand projections. One is the baseline projection, which suggests that steel demand will grow to about 2.5 billion tons in 2050 from a bit less than 2 billion tons nowadays. And the second projection is the Sustainable Development Scenario projection, where efficiency gains in steel use and the impact from circular economy adoption is factored or are factored in. And what we see, for example, in the green part, in the construction sector, or the construction sector's demand for steel declining by about 200 million tons when compared with baseline demand projection, thanks to buildings having longer lifetimes or buildings having more materials efficient designs or circular designs. Similarly, the yellow and orange parts in automotive, the IEA estimates a demand reduction of around 100 million tons when compared with the baseline scenario, thanks to adoption of shared mobility business models and also lightweighting and more materials efficient vehicle designs. And all these efficiency gains and circular economy adoption brings down the estimated demand from 2.5 billion tons to around 2.1 million tons. But we see great uncertainties here. First of all, circular economy is developing rapidly. However, it's not really easy to envisage what the impact will be in 10 years from now, in 20 years from now. Currently, the impact is quite low. So circular economy impact on materials demand is starting from a low base, let me put it like that. And secondly, it's possible to imagine other scenarios under which steel demand would be higher than the steel demand, the sustainable development scenario projection. For example, under a scenario in which climate change impact becomes severe, many countries would accelerate their climate change adaptation efforts, and that would probably boost materials demand, including steel demand, globally. So when we look at it from that perspective, probably over the next 3 decades, global steel demand will be anywhere between 2 billion tons to 2.5 billion tons. And to achieve the decarbonisation targets by 2050, the industry should reduce its emissions intensity by at least 60%. So if we are facing a 2.5 billion demand future, then probably the reductions should be much bigger at around 80% reductions in emissions intensity would be required. So this is the challenge faced by the industry, but this is also one complexity in front of the whole value chain. So what kind of a future the value chain should prepare for, a 2.5 billion steel demand world or a 2 billion ton steel demand world? Growing scrap availability. We estimate that obsolete scrap availability will be growing by around 500 million tons by 2050 over the next 3 decades, which will be enough to produce about 450 million tons of steel from scrap. So that's why scrap availability will be a great help, let's say, to steel industry in its decarbonisation challenge. And we don't see a big uncertainty here because scrap availability is by and large a function of past consumption. However, we see several issues which might complicate, let's say, the recycling activities. First of all, the growth in scrap availability is concentrated in the developing world, and that's why bringing growing availability as supply to domestic and international markets would require development of recycling infrastructure and the recycling industries in a timely manner. Secondly, we observe a deterioration trend in scrap quality, probably stemming from steel-containing goods designs becoming more complex, more multi-material, and higher alloyed, usage of higher alloyed materials. For example, electrification, or because of electrification, copper content in steel using goods is increasing considerably, and copper is one of the tramp elements and is causing already some difficulties in recovering and recycling the FE units from steel-containing goods. And thirdly, international trade. International trade has so far helped achieving an optimal global distribution of scrap, ensuring the movement of supply from those countries with surplus scrap availability to those countries with, that are short of scrap. But as the importance of electric steelmaking grows and as the importance of scrap grows as a green material, we see many countries considering scrap trade restrictions, which might lead to suboptimal allocations of scrap availability globally. And these kind of issues I'd try to address with Jeremy during the panel session. And the third lever, the development and deployment of breakthrough technologies. So what's the scale of change we are talking about? We again turn to the IEA study. The 2 bars on the left-hand side show the 2009 steelmaking structure and the structure projected by IEA, steelmaking structure, for the year 2050. Those gray parts on top are the electric steelmaking based on scrap. We see that doubling from a bit more than 20% nowadays to around 40%. The blue parts at the bottom are the BF-BOFs, which represent a share of more than 70% nowadays, and we see that share halving to around 35%. And we see the share of more innovative approaches growing to around 30-35% in 2050, about 20% of which is direct reduction and about 78% direct reduction based on 100% green hydrogen. So so we now have several roadmaps available for steel industry decarbonization, and IEA one is one of the, let's say, more moderate ones, but even this one projects a massive change or a drastic change in steelmaking structure globally. So what kind of constraints and uncertainties we are seeing here? Financial constraints, as we've heard during the last session. Construction constraints. So, for example, IEA's projection requires that as from the year 2030, every month a new hydrogen-based or a new direct reduction facility should commission, and a new CCUS facility should commission almost every 2-3 weeks. So is there enough technology provider capacity for that? Is there enough contractor capacity for the construction of these facilities? What about labor shortages and cost? Energy constraints. The transformation of steel making requires massive amounts of electricity, growing electric steel making, and also green hydrogen production. And hence, targeted and accelerated expansion of green energy generation capacity is the single most important enabling condition for steel industry's decarbonization. Raw materials constraints. Again, according to the current, nowadays there is about 100 million tons of direct reduced iron production. But according to all these steel industry decarbonization roadmaps, DRI production is expected to triple or quadruple. So will there be enough direct reduction grade raw material to meet such a massive growth? Out of the 2.3 billion tons or so iron ore consumption nowadays, only about 150 million tons is direct grade. So will there be 450 million tons or more direct grade material, iron ore, available in the year 2050 is an important question. And these kind of iron ore related questions we'd like to expand on together with Mihir. But it's not only iron ore. Will there be enough natural gas to support the growth in direct reduction? In some facilities permanently, or in other facilities as a transition fuel towards 100% green hydrogen steel making. Lastly, development and optimization. When we talk about development of a breakthrough technology, actually we are talking about development, optimization, and streamlining of numerous processes. For example, for hydrogen steel making, we are talking about development, optimization, and streamlining of large-scale transportation, storage, and containment of hydrogen, gas recirculation, treatment, melting, and refining of carbon-free DRI with high gangue content, plant design, and process balance. So all these numerous processes will need to be developed to achieve the hydrogen steel making, green steel making by using hydrogen. To conclude, well, obviously we are faced with a race against time, and that's why we require the most efficient approaches, most capital efficient, most energy efficient, and most time efficient ways of decarbonizing steel making. Secondly, constraints we are facing are real and do have the potential to slow down steel industry's decarbonization process, and hence we need to discuss these problems with all steel value chain stakeholders and establish green steel partnerships to overcome such challenges. And hence, we should promote dialogue across the steel value chain. And lastly, this is obviously a steel value chain transformation. It's not, these transformation cannot be achieved in an unconcerted manner or only one part of the value chain transforming, but the others continuing operate their operations in the business as usual manner. So a successful decarbonization process requires a concerted transformation from raw materials and energy supply to the usage of and recycling of steel containing goods. So this concludes my scene setting presentation. I'd be happy to take any questions. Thank you. I cannot see any hands raised, so maybe we can immediately move to the panel part of this discussion. So I'd like to introduce and start with Rutger. And first, introduce Rutger. Rutger is the CEO and the founder and CEO of Kobolde, a company that provides systems for optimal use of raw materials for steel and other metals industries. He is also a researcher and a teacher at the Royal Institute of Technology in Stockholm. And Rutger published a series of articles on decarbonization of the global steel industry over the last 3 years. And during this panel, I'd like to ask him share some of his main ideas from these articles. Shall I continue? I think I should continue with the introduction and then start with the questions. So next we have Jose Noldin. Jose has 25 years of academic and commercial experience in iron ore making technologies and processes. And he's now the CEO of Gravity, a green iron making startup. So we'd like to hear from him the perspective from the green technology developer, the key challenges and opportunities they are seeing. And also during the last panel, we heard about the absence of a business model. So maybe we can talk to us or share with us your opinion about the ideal green technology development or green iron making or steel making business model. And next, we have with us Paul Butterworth from CRU. Paul has about 30 years of experience in steel sector, in economic analysis, environmental affairs, strategy, operations, and he is currently leading CRU's research activities on sustainability. And with Paul, Paul also published several articles on the important factors that will be influencing or shaping the decarbonization process of steelmaking. One of them, which I find quite interesting, is on the green electricity and green hydrogen availability and cost in the future. So we'll be starting with that topic with Paul. And next we have Mihir Vora from Wood Mackenzie. Mihir is one of the key persons behind WoodMac's steel sector decarbonization roadmaps and projections. And with Mihir, we'd like to expand on the iron ore requirements of steel industry's decarbonization. And last but not least, we have Jeremy Jones. Jeremy is the founder and CEO of CIX, a company that helps steelmakers improve their performances globally. And Jeremy is one of the most renowned experts globally in electric steelmaking. So here we have some of the thought leaders, in my opinion, of our industry. So thanks for joining us today. So let me start our panel with Rutger. Rutger, I mentioned about your articles that you published over last 3 years. I think it's the first one, titled as Between a Pony and a Pink Unicorn, right? Okay, so there you argued that decarbonization approaches that involve leaping forward to breakthrough technologies are surrounded by considerable uncertainties, some of which I tried to touch during my presentation. And you also argued that more gradual approaches actually have quite important advantages, such as bringing emissions reductions sooner, using the currently installed capacities for longer, and allowing the value chain to giving them time to adapt. So can you share your ideas with us and expand on these ideas, please? Thank you.
Thank you, Boris. So why did I say that? How come I came up with these conclusions? Well, when I was a PhD student in the 1980s, Europe had just gone through an energy crisis. And the steel plants in Europe were in a terrible condition. And I think it was a little bit the same in the United States. So everybody thought, what shall we do? We have to replace them. We can't close everything and not build anything new, but a coke oven plant is so expensive. A sinter plant is so expensive. But there's a solution. It's called smelting reduction. So we can do this, we can do that, and a number of process suggestions actually came up. I think there were between 30 and 50 different. We have 5 different process solutions in Sweden, but all over Europe they worked with these. And my job as a PhD student was to make economic calculations, comparing these processes, looking at them and saying which one of these will actually eventually survive, what kind of processes will we have in the future. And the peak of my career in that day was standing in as a speaker in Jamshedpur in India, in the conference Iron and Steel, New Ways to Iron and Steel Under Indian Conditions. And I explained to everybody in an exquisite manner how all these new processes would change their lives, and the blast furnace was perhaps not going to survive very long, because they all outperformed the blast furnace, at least on paper. And how wrong we were. Because what happened was that the blast furnace changed. And what we underestimated was the advantage of an existing process with actually a plant in operation, with people and researchers knowledgeable about the process that could improve it. And so, first of all, the energy consumption in the blast furnace went down, and the cost for erecting new plants also went down, and the blast furnace stayed competitive. And I'm not saying, I'm not singing the praise of the blast furnace, but I think it would be ignorant of us not to take that type of experience into consideration. So I gave a presentation on this at a small seminar, and with me was this guy from a consultancy company in Sweden. He was responsible for designing the new Swedish high voltage electricity grid. And he then said, what the industry now is promising the politicians is something between a pink pony and a unicorn. And that was actually in Steel Times International changed to between a pony and a pink unicorn. But that's okay. I actually had that in the picture with me and a pink unicorn and a pink elephant. Because the last sentence in that article was, don't forget the elephant in the room. The elephant is the actually huge installed base of blast furnaces. And actually, it was rather basic ideas. But an installed process existing has a great advantage. So what situation do we have now? We have 2 main processes that might be reasonably low carbon, and that is a blast furnace if you improve it and make it with oxygen, top gas recycling, and CCS. That is easier to do with something that's already there. You may not like it. We don't solve the problem with the methane coming from the carbon sources. I totally agree with that. But if it's reasonably good, and then it's there. And the other is actually taking the gases reduction with natural gas and CCS. And that is the solution that I understand my friend from GFE has gone for. And it's a solution that exists today, that you produce the DRI where you have the natural gas and the possibility of CCS, and then you ship the DRI. What is important now, and I will finalize that, what is important now, that these 2 could be used as some sort of baseline from a cost and carbon footprint point of view, because they will be there. They will definitely be there. And they will be fairly cost efficient and fairly CO2 efficient. So all these new processes that we are talking about, and I really wish everybody luck, and especially Jose, but I really wish them luck, but they have to produce DRI or molten steel at a cost level and a carbon footprint that is not much above what you have in the basic technologies. And actually, that is what I think we have on competitiveness in the future, what the demand we have on the new technologies.
Thanks a lot, Rutger. And by coincidence, we have Jose next. So Jose, really, as I've said during introduction, what's your view on Rutger's arguments? And as the CEO of Green Iron Making Technology Developer, what's your opinion on the key challenges and opportunities? And again, this business model, or the ideal business model, is it absent or it's already there?
Thanks, Baris, and good afternoon to everyone. Congrats, worldsteel, for the organization of the event. I know it's quite a lot of work, but unpackable, so very nice to be here, and thanks for the invitation. So yeah, indeed, we see a lot of challenges, so you're not alone. I'll come back to the challenges a bit after, because really it's about opportunities. 15 years ago, we were discussing who would be the last man standing in Europe, because we all more or less had an agreement that in Europe there wouldn't be steel production over time. And I believe what we are seeing now is totally different. What we are discussing now is how we're going to make it, how we're going to transform it with the different opportunities that we have out there. I believe we have something which is quite unique. We have a sort of a tailwind that is forcing us to move ahead. First, we have acceptance by society. There is a recognition that climate change exists. There is recognition that the cost of inaction is actually much higher than what will cost us to do it. And maybe dragged by that, we have a combination that it's unique in the history of our industry, which is an alliance between business, government means policies, and finance. I believe the financial world is alert and is moving into the right direction. And then based on this opportunity, this let's say alignment of planets that our shareholders under the initiative of EIT InnoEnergy, which is a European private-public structure to accelerate the energy transition, the decarbonization of the different industries. They realized, they identified a sweet spot, which is we need to decarbonize steel just because we need a lot of steel in the future. Someone said in the morning, and I can only repeat, every windmill, 2,000 tons of steel, 3,000, 4,000 if it's a big offshore wind. Electric vehicles, a lot of steel will be needed, but makes no sense if we have to feed those industries with a material that today emits 2, maybe more tons of CO2 per ton. So we need to decarbonize. So it's a sweet spot. But we have good news. 80% of those emissions are in the iron production part. So there is the creation of this value pool in iron making. I believe that's what the opportunity that our shareholders identified. But there are many challenges. And the challenges, we are following an approach of collaboration. So basically what the company did was teaming up. So we have in the cap table what you see on this slide, people that will help us in unlocking the different challenges. So to make iron in Europe, you need a good site with good logistics. So we have EDEC, which is a real estate operator in France. You need a lot of electricity. I'll come back to that. We have ENGIE. You need the technology for hydrogen production, so we have Plug. We have DRI technology. Then we have Primetals. And we have to show that the market is there. And then we have a Forvia in the cap table, which is a tier 1 supplier in the automotive industry, which is committing to say, I want to decarbonize my scope 3. So a lot of those contracts that the colleague from Bloomberg, he showed that out of the 48, I can guarantee you 47 maybe, this is a result of pledges done by the different companies. So they are pledging to decarbonize, and they are willing to put the money where the mouth is, and committing to buy material at a premium. And the big thing for us, for Gravity, is that we are going to focus on the iron production. And why? For a very simple reason. For the last 300 years, we have been exposed to a global commodity that what was feeding, let's say, steel production everywhere. So to make iron in the beginning of the century was to be close to a coal mine. Then later we decided to move to the coast because it was important to have logistics. We believe that in the future, iron needs to be produced where electricity is. We are moving from million BTUs, from coal, natural gas, oil, to kilowatt hours. But that's a big difference, because a global commodity means that if there is a flood in Australia, the coal prices in the US change. If there is a problem now, if there is a problem in Brazil, because we don't have enough rain and the electricity prices in Brazil explode, it will be unaffected in other countries. So, and that's a big difference, changing from a global commodity to a regional commodity. And then I come to the challenges, lots of challenges. Technology is a challenge. It's an innovation. We are going to produce iron based on 100% hydrogen. It's a new product. No one really knows how the material will be stored, will be transported, will be utilized. But the key challenge for us, and I would say for decarbonization in general, is to have access to electricity. Low carbon, available, and competitive. Again, low carbon, available, and competitive. And I'm actually surprised that it's already 4 o'clock in the afternoon. I still haven't heard the word nuclear today, which is a big discussion. I would love to have that, because, guys, we need massive movements and investment on electricity. So many opportunities. I see 3 main challenges: electricity, electricity, and electricity.
So nuclear is the second elephant in the room, I guess, but we'll leave that to other open forums, I guess. So yes, electricity, energy. So first of all, thanks a lot, Jose. And with that, Paul, as I've said, you also published several articles, and one of them was on green energy availability and cost. So can you please share your main findings and expand on the implications for the steel industry? Thank you.
Can I use that? It'll probably be easier. That's the green button, is it?
Yes, it's the green button.
So I was actually asked to talk about hydrogen, and then Kwasi, you've spent a lot of time talking about hydrogen, so there's a lot of overlap, but I do disagree in some places, so maybe that's a good thing, and there'll be some discussion about that. The other thing I wanted to say before I started is I'm quite a simple person. I've been in the steel industry over 30 years, and for me, what's been important is cost. If you don't get your costs right, you can lose a lot of money very, very quickly. And the energy transition is about cost. We've heard it a lot already, but cost is very, very important. So if we don't get it right, it's going to cause a lot of problems. This is really sort of a lead into my presentation. There's a legal thing there. I don't actually know what it says, but I'll start off. And this is where I'm starting to disagree with you already, Kwasi. It's about the cost of hydrogen. You hear a lot about how hydrogen is going to cost $1 a kilogram. It's going to be really cheap, and steel making with hydrogen is going to be so cheap in the future, we don't even have to worry about it. If you work through the numbers, then to have hydrogen at $1 a kilogram, even if we ignore the electrolyzer capex and ignore the OPEX, non-power OPEX of the electrolyzer and solar, for $1 a kilogram, you need power at $9 a megawatt hour, okay? $9 a megawatt hour. That means the solar capex would have to be about $190,000 per megawatt. Current solar capex is about $1 million per megawatt, maybe a bit less, 950 I've put there. Just buying the raw materials for that solar, the lumps of steel and the lumps of aluminium, cost about $170,000. Okay, so for me, it starts to feel difficult that we're going to get down to electricity prices, which Jose's talking about, of those sorts of levels. It's going to be difficult, I think. This is our view of, I've just put solar in, it's in Europe. This is our view of what solar costs might do. It's our forecast, and you can question it, and I can talk about the assumptions. We've essentially assumed more than 100% increase in efficiency of a solar panel. That reduces the capex. It brings costs down. You can see, though, there are two lines there. We've heard a few times people say renewable energy is cheaper than fossil energy. I don't actually agree with that. Maybe it's cheaper than fossil energy today in an energy crisis. Maybe they're comparing variable renewable energy, so a solar plant which is giving out a lot in the middle of the day and nothing at night, and they're looking at that variable cost. I've got two lines. The lower line is the cost of the variable output. The upper green line is if we have some storage, which means you can make it a continuous supply, which is what you would want to compare on a like-for-like basis with a combined cycle gas turbine or something. Now, this is important, and maybe it goes back to what Jose's talking about. I do mention nuclear, actually, Jose, in a minute. If you're looking at the lower line, the cost of that one, that's variable renewable energy, you'd have to build a very large electrolyser to absorb that variability, an electrolyser that won't be operating for most of the time. If you want continuous power, and then you build your electrolyser at the size you want the upper line, it's more expensive. But none of them are down at $9 a megawatt hour. Is the key thing here. So on the left-hand chart here is our forecast, our view of hydrogen costs in Europe. There's a pink line on there, which is our view of pink hydrogen, based on nuclear. But we've got green, grey and blue. On the right-hand side, I've just done what I would say the calculation is for hydrogen costs today. So a solar plant costs about $950,000 per megawatt. You've got the solar OPEX. You've got a choice about whether you have some storage and you build your electrolyser at the right size, or you don't have storage but you oversize your electrolyser. That'll be an economic decision. You've got electrolyser non-OPEX costs. When you work all of that through, hydrogen is about $6 a kilogram. $6 a kilogram today that works out at $55 a gigajoule. That compares with a metallurgical coal price of about $3 a gigajoule through the cycle, steady state, after giving credits for processed gas. It's a massive, massive cost difference for your main reductant in making steel. That's a difficult thing. That's a challenge. That's a challenge that we face as an industry to make that work today. Now, even in the future, by 2050, we think we're not going to get much below $2.50 a kilogram for hydrogen. That's at the electrolyser. It doesn't include storage costs, distribution costs. You can probably add another $1.50 for that to get it in a usable state at the steel company. So it's a challenge. That is a challenge that the steel industry faces, and it's a cost one. And as I said, cost has always been very important to me in the steel industry. It's been a key thing for survivability. If we push all of that through and say, well, what does that mean then for building hydrogen-based steel plants? The left-hand chart is our view of what the CO2 price needs to be to raise the cost of fossil-based steel making to such a level that hydrogen-based steelmaking becomes a viable economic alternative. Today, I think that's over $200 it needs to be, with no free allocation. This is in Europe I've done it for, assuming no free allocation, over $200. And even by 2050, it's still at $160. That's what the price of CO2 needs to be to lift the cost of fossil-based steelmaking. Now, you can also convert that in and say, well, what does that mean in terms of premium? And what it means in terms of premium is, I think a buyer would have to pay 60% premium today, over 60% premium for steel to cover the costs of that steel, 40% in the future. If it's subsidy, I think it's like about $20 billion a year today for the European steel industry. That's the order of magnitude of cost that we're talking about. The right-hand side is our forecast for the carbon price in Europe, and you can see it crosses over in about 2038, 2040, something like that. So we would argue that it's not until the carbon price gets that high, and we think that's going to be in the late 2030s, that hydrogen-based steel making, H2 with DRI and electric arc furnace, becomes a viable economic alternative. Before then, it's not competitive without subsidy, without premium, or some mix of carbon price, subsidy and premium. This is my last slide. The left-hand chart shows our forecast for carbon emissions from the steel industry globally out to 2050. The dark line. The dotted lines, or the dashed lines, are the IPCC temperature pathways, 1.5 degrees to 2.5 degrees, 3 degrees. We believe that the steel industry into the middle of the 2030s and a little bit beyond to 2035 is on a plus 3 degree pathway. That's where we are. This is taking into account all of the projects that have been announced. It's taking into account the extra scrap that is available. It's on a plus 3 degree pathway. Now, what I would argue, and it sort of goes back to some of the things that have already been said, hydrogen-based steel making, H2 DRI with an arc furnace, is hardly going to impact on that emissions because we're not going to build out sufficient capacity in the time to have a significant impact. Scrap is not going to impact on that because we've already taken into account the additional scrap that's available. Those are not solutions for that, and that's eating up the carbon budget incredibly quickly. And in fact, we would argue that the carbon budget for a 1.5 degree under that profile is going to be gone before the end of this decade. So 1.5 degrees is not going to happen, almost certainly. 2 degrees is at risk. What we need to do is, in my view, is to try and reduce that today. And that's not about H2 DRI, EF. It's not about scrap, because it's already in there. It's about what Rutger says. It's about what have we got today and what can we do. You mentioned the Step Up programme, and I saw a 15% reduction. I think there's a lot more that can be done with existing assets in order to get those carbon emissions down. And I think that's where the focus is to deal with this. Whereas I do believe the future will be a hydrogen DRI type, or it will certainly be part of the solution, but it's not going to help in this situation. Is that?
Thanks, Paul. Quite
depressing?
Alarming. I should say alarming. But do you expect to see any changes soon, which would bring some of these curves down, Paul?
Well, no, I think there is an issue about the speed that there are challenges, that the policy isn't in place, the policy structures are not in place. There is a cost effect, there is a cost challenge here, and it needs to be overcome through policy. That's either protections or subsidy, and there are things happening, but it's not enough. So I don't see that happening, and as I say, scrap isn't going to affect that because we've already accounted for the extra scrap. So no changes in that respect. I don't think there is a solution coming from that direction in that period that I'm talking about there. Longer term, yes, but because we're eating up the carbon budget, I think we need to do something more quickly, which gives us more flexibility down the line to deal with the other emissions. Yeah.
Thanks, Paul. Quite clear. So, Mihir, I turn to you for some good news, finally. So what do you see on the iron ore front? The iron ore requirements for potential, let's say, steel industry decarbonization roadmaps. What kind of changes we might expect to see in the iron ore supply structure? So, thank you.
Yeah, thanks so much. Let me first start by speaking about the demand and supply for DR grade pellets. I think we've all been talking more about hydrogen DRI, right? So, if the way steel decarbonization is going and the way we are expecting that, our base case is a little lower than what Paul mentioned. We are expecting anywhere between 2.5 to 2.7 degrees in our base case, the temperature rise over the end of the century. We expect the demand for DR grade pellet feed would increase 2.5 times from current levels, nearly about 400 to 420 million tons by 2050. And if I put things in perspective, if I go to the 1.5 degree scenario, the numbers, amplify. They just go about 750 million tons. If you look at the current supply that is out there, if you look at the prime grade supply, as we call it, which is 67 Fe iron ore with less than 4.5% impurities, we are definitely going to have a challenge. We don't have enough supply. So there is an alternative that's available. There is moderately rich grade of ore that is available, which is at 65 Fe, but again, impurities need to be less than 4.5%. That will ease in, or basically, I would say, loosen up the supply a little bit, but that will come at an additional cost. We have to do beneficiation to bring the 65 Fe up to 67. That still doesn't bridge the gap between the demand and supply that we are seeing. In that particular perspective, then the iron ore miners will not be left with much options. They don't have a single silver bullet to kind of, take care of the supply to the kind of demand that we are looking at. And in that scenario, multiple options need to be evaluated. I think the first option for iron ore miners would be to kind of look at, investing into newer mines. The lead times are incredibly high. Like, you start investing into a mine right now, you'll start production only 10 years down the line. So the lead times are high, so that needs to be taken into perspective. And as Paul rightly mentioned, that something needs to be done right now. So there are some initiatives. For example, Rio Tinto has invested with, in Simandou, that is going to increase their portfolio share of high-grade ore production to about 25% from the current 5%. FMG has 0%. High-grade ore production in their portfolio because they're operating in Australia. But their Iron Bridge project and the project that they're running out in Gabon will actually increase their high-grade ore supply to about 12% of their overall portfolio. So those kind of, newer projects need to be kind of commissioned, invested into right now. The next option is probably what, let's say, Vale is doing. They already have rich grade of ore that is available with them, and they are kind of doing pelletization and briquetting in order to make that ore usable. And eventually, I think, it will lead to some of the miners, even some of the steel makers in the room here, getting into the green metallic space. I'll just cover that later. The third option is probably, you need to have like a combination. You have BF grade pellet feed, which is anywhere between 62 to 64 Fe. You can do beneficiation, increase 1 or 2 percentage points on the Fe part, but that doesn't really get over the line when it comes to DR grid because the impurities are high. And that's where there are some newer technologies which are being currently researched on, and we are quite bullish about the melting technology. Even the miners are bullish on that if we are able to kind of melt DRI and take care of the impurity content in DRI, then we might reach a stage where supply matches the demand. So multiple things need to get into perspective. All the pieces of puzzles need to fall in place in order to reach that. And from a supply standpoint, where will the supply come from? Obviously, Brazil stands in the pole position right now. They have their own issues with environment, with weather and stuff like that. But they have good grade of ore that can actually be used for DR grade production. Then there are newer projects like Simandou and Iron Bridge in Australia, which I'm talking about, which it can elevate supply. But for someone like in Australia who has dominated the iron ore production till now, they will have to look at not just beneficiation, but a combination of beneficiation and DRI melting, and eventually get into a position where they start forward integrating themselves into the green metallic space. And that's just the second part of my answer here, where we believe that Australia, along with regions like Middle East, will stand a very good potential to kind of develop metallic hubs. And these metallic hubs will eventually come up by the end of this decade and kind of alter the supply chains in a sense that these DRI hubs, for any DRI hubs to come in, as Jose rightly mentioned, that there needs to be abundant electricity, abundant renewable electricity if you want to make green DRI. So, regions like Australia and Middle East do have those kind of things in perspective. They have gas availability. So there is an abundant amount of gas so they have an oversupply of gas which can actually be supplied to the industries after it goes through the power sector. So they have that. Along with that, there are investments which are happening. Let's say in Middle East, there are investments happening on the pelletization front. In Australia, there will be investments eventually happening on the beneficiation front. So these kind of metallic hubs, once they come in, they can start supplying to the energy transition requirements of more mature economies like Europe, like Japan. China will also come into the fray. I'm not saying that these regions will not have their own DRI production. What I'm saying is that they will not have enough DRI production within themselves and have to eventually rely on importing HBI. Because policies like EU CBAM they're kind of going to hamper the finished steel trade in the entire ecosystem. And once CBAM starts kicking in and really hurting the pockets of steel makers, which will eventually happen in the early years of 2030s, the finished steel trade is going to get impacted. And we believe that there is an opportunity for HBI trade to kind of come in. You produce green HBI, you supply it to these regions who are looking at decarbonizing quickly, and eventually, have a more concentrated EAF production. So the overarching theme is miners need to forward integrate. Along with that, even steel makers, we've already been seeing a lot of joint ventures happening. Steel makers will kind of backward integrate. So it's a win-win for both the value chain members. Finished steel trade is definitely going to get impacted anywhere between 80 to 100 million tons over the longer term in our view. And that 8 to 100 million tons will actually go in, let's say, an HBI trade. We believe that over the longer term, that kind of a number is viable for HBI trade, barring the issues that the industry is facing when it comes to shipping or something like that, barring that. And I think the final part, which Paul also touched upon, was cost, where even I would want to touch upon that. If I compare a like-to-like EAF production in the EU, where EU manufactures DRI and also manufactures EAF locally, their overall cost of production will be anywhere between 15% higher as compared to if they import DRI from the Middle East and they produce EAF locally. So that kind of things will just get amplified when we move to regions like Japan and South Korea. They will find same kind of benefits importing DRI from Middle East, importing DRI from Australia. These benefits might even amplify to about 15 to 20% in terms of cost if they are, if they're made at the right cost. So, the challenge is huge. But as I mentioned in the first part, I just want to conclude with that investments need to start happening now.
Thanks a lot, Mahesh. And lastly, Jeremy, scrap, where we see a great opportunity, but also some difficulties. So can you please explain and also help us understand how to mitigate such difficulties?
Yeah, so is this working? Okay. So you see here, I've got a number of logos here. So my company is CIX, but I'm also the technical advisor to the IIMA. Some of you might be aware of IIMA. It represents all of the merchant producers of DRI, HBI, and pig iron. It also represents all of the major iron ore suppliers. So it's a group that's very, very focused on what we call ore-based metallics. And I'm actually going to show you the synergies between scrap and ore-based metallics. So if we look at scrap as a decarbonization lever, 100% scrap-based operations currently using EAF technology obviously already have a very low CO2 footprint. So for certain product lines, notably rebar, merchant bar, structural steel, you can use 100% scrap, very little difficulty meeting your product requirements. SBQ, a little bit more difficult, because sometimes you're going to want to produce maybe a 10 to a 15 copper product, and then you're going to use a little bit of ore-based metallics to just push down that copper level in the product. Now, the footprint can also be lowered through improvements in efficiency and things like iron yield. Very few people talk about iron yield. As a steel maker, my metallics that I'm putting in the furnace, all I'm really interested in is the Fe. If you could supply me with 100% Fe material to put in my furnace, I'd be very happy. I could make any product. I could be very cost effective, okay? So people sometimes don't think about, okay, what's really important from a steelmaking perspective? And hopefully we don't lose sight of that as we start to try to decarbonize the steel industry. Huh? There's some irony there, yes. In order to truly use our raw materials effectively, we have to understand the properties of that material. We need to have a way to measure the value in use, the capability of that material, and then also understand the process well enough to maximize that value in use, okay? So one of the major issues is increasing levels of scrap residuals. So for those of you that aren't steel makers, things like copper, tin, nickel, and moly are a concern because it affects the formability of steel, depending on what products we're making. And so in order to dilute these, as we recycle scrap, these get more and more concentrated. So in order to continue to recycle scrap, we need to also have a balance with ore-based metallics. So when I look at the scrap challenges, one of the largest ones is the rising residual levels in scrap. Another one which people don't pay attention to is dirt, gangue, and silicon content of scrap. This has a huge impact on the carbon footprint, and I'll show you an example that I presented last year, and when people saw it, they didn't believe it, okay? The non-metallics content of the scrap, and mostly those materials, whether it's oil, grease, paint, coatings, it creates environmental problems. We don't want it there. We also have an issue with the lack of definition of scrap characteristics. Several years ago, I worked with Henk and Rizwan. We had a group in worldsteel called the EAF Experts Committee. And what we did was we started by trying to create a matrix that showed what we call different grades of scrap in different parts of the world. Because when you see a lot of material that's exported, and scrap export is a huge global industry now, I can tell you that it's like night and day. When I first started working with Çalıkoglu in Turkey, they were getting up to 7% dirt in their scrap. That's not uncommon in exported scrap. And then things got even sort of fuzzier when we created this mixed number 1 and 2 heavy, which doesn't really exist. People always show me material that's supposed to be mixed number 1 and 2 heavy, and it's a joke. They say, well, it's 80% number 1, 20% number 2. But it has a copper content of 0.6. 100% number 2 should never be above 0.55, so mathematically, I don't know how you get to 0.6 when you mix in 80% of what's supposed to be better scrap. It's very confusing to me as an engineer and a mathematician. We also don't have good definition with respect to value in use, and I'll show you some of the tools that we've developed to help people to understand this more effectively. Because if you really don't understand value in use as a steelmaker, then it's difficult to make really good decisions and especially plan for long-term decisions with respect to raw materials. And then another potential issue is the scrap availability in close proximity to the steel plant. So as Bar showed in the projections out to 2050, this becomes less of a problem in the developing world out towards 2050 because we start to get more scrap coming back into circulation. In the developed world, we already have lots of scrap. We tend to export scrap. So, you know, until recently, the EU exported scrap. North America, we export 20 million tons a year. Japan, you export scrap into Asia. But we have to be cognizant of the logistics and the impact also on carbon footprint. Now, by 2050, when we have electric chips, electric buses, electric trucks, electric rail, everything, I guess it's not a problem anymore. But for now, it still can represent anywhere from 10 to 20% of the carbon footprint of steel production in some locations in the world. So we can't just ignore it because in 30 years, it won't be a problem. We need to pay attention to those things. Now, fortunately, we have technical solutions right now. We know how to deal with dirt, gangue, in scrap. And this isn't only a problem for scrap, it's also a problem for ore-based metallics. But we have ways of separating dirt from scrap. As I said, when I first worked with Çalhanoğlu, they were getting 7%. We reduced that below 1%. And the equipment was paid for in less than 6 months, based on the savings. Similarly, the non-metallics content, we can separate that. We can do a better job of defining our scrap characteristics and what's important. And we have the ability to quantify and determine the value in use. Some of the other issues, like the scrap availability close to the steel plant, okay, that's still a problem for some parts of the world. And the rising residual levels in scrap is still a big concern. But when we look at rising residual levels in scrap, we have to differentiate between contained copper and free copper. So free copper is things like when I shred an automobile, I have copper wires and other things in there. It gets mixed in. It ends up going into the furnace. It gets melted. Now it's in the steel, and I can't get rid of it. But we have technologies now implemented both here in Europe and also in North America where we can effectively produce shredded scrap at about a 0.16 copper consistently. So that's very important. And all of these things tied together, we talked about one of the major things to decarbonize is we have to have efficiency and we have to have consistency. And those are the same things that allow you to optimize a steel plant. Typically, when you improve consistency and improve reliability, you see up to a 30% improvement in productivity. Okay, that's based on numerous plants that we've worked with around the world. Now, just to give you an idea of the impact of 1% dirt in the scrap. So we did a comparison for a 1 million ton a year plant with scrap at 2% dirt and scrap at 1% dirt. These are very, very optimistic numbers. Most people right now are probably dealing with 3 to 4% dirt if they're lucky, okay? So what happens is those represent acid components of the slag. We have to offset those with basic components of the slag by adding fluxes. And the cost to the steel plant, when you look at the increased quantity of slag generated, you look at the extra energy required, the yield losses. This is going to cost this plant, what was it there? Almost $11 million per year. So that's essentially $11 per ton of steel produced. Now, to put that in perspective, give me half of that, I'll be very happy and I'll be on a beach somewhere. Right? So, and more importantly, and we were surprised nobody had done this kind of analysis before, and this again is very conservative, we increased the CO2 footprint by 43 kilos per ton of steel. So if you're a plant that was getting scrap with 7% dirt, you're producing an extra 280 kilos of CO2 per year based on that. And you're wasting energy and you're wasting yield. So should we pay attention? Well, yeah, I think that is something that's very important. To me, it's obvious. I'm just having trouble convincing everyone else. Oops. Now, another pet peeve I have is with regards to scrap circularity. Circularity to most people seems to mean scrap processor tells the steel plant what they can have. The customer buying from the steel plant tells them what they need to get. And the steel guy tries to figure out how to match those two, okay? But if we're talking about true circularity, and this is where all of these ESGs can start talking to manufacturers, then everything that is manufactured should be designed for end of life and designed for recycle. So that means when you have an electric car that has 6 to 8 times as much copper in it as a conventional car, basically the way that the car is laid out, where the wires are, where the copper battery is, all these things are designed in a way that they can easily be removed before that car goes into a shredder. To me, that's just common sense. We also have an idea within our group that appliances should have a QR code. You scan it, it tells you exactly, remove this screw, this screw, take this out, take that out. And again, now you're optimizing. And the problem is that manufacturers don't realize by not doing this, they're making it more difficult for the steel maker to provide them with the product that they want. And it means you're using more energy, more resources. All of these things are tied together. So this is a concept that we have to get people to change their mindset. And that's really what it takes. It's not that the technologies aren't available right now. It's just that people don't have the mindset to apply those and understand how it's affecting things in this circularity of scrap. So as I said, we've developed a very comprehensive value and use model. We actually use this for several of our steel clients to help them optimize and track scrap quality, make their purchasing decisions. If anyone's interested, I can show you a lot more detail about it. This is a chart I put together several years ago. I think I did this for one of the Ramco presentations. And what it shows is the average copper content in scrap on the vertical axis, and along the bottom, the maximum copper level allowable in the product that you're trying to produce. And what it shows is the yellow lines show where people think we are right now, around 25 to 30 points of copper average across all recycled scrap. So what it shows is that if you're trying to make automotive products, really the only solution we have right now is to dilute residuals with ore-based metallics, which have no copper content or essentially 0.002. But what's very scary is if you look at the red line, which is there have been several papers that were put out here in the EU that project that by 2050 we're going to be at 0.5% copper on average in scrap. And you can see that even if you're producing rebar, you have to use some ore-based metallics. Now, if we're smart about how we process scrap, and essentially, let's focus on producing green scrap. You put good inputs into the steel process, you get good outputs, okay? And what people don't realize, it actually can save energy, it can save yield, so it has a lot of benefits. Yes, it costs some money to do this, but the benefits outweigh the cost. Most people just aren't aware of that. So we have to drive towards producing a cleaner, better raw material input to steelmaking. This allows us then to conserve resources on the iron ore side of things. Scrap still plays a critical role, but there's a synergy. Ore-based metallics are an enabler that allow greater recycle of scrap. And so we have to recognize these synergies between the different sources of metallics and balance those and use them in the most effective way in the steelmaking process. So I think that's the last one. Yep, that's what
Thanks.
I've got.
Thanks, Jeremy. This brings the first round of the panel to an end. Actually, we had a second round, but we have only about 13 minutes left. So I'd like to turn to floor for questions. But before also, I'd like to reiterate some of the, let's say, key ideas I heard from the panelists. Well, first of all, as global steel industry, we are eating up our carbon budget very, very quickly. probably this is not unique for us. Probably this is the case for many, many industrial sectors, at least maybe for all economic systems. Secondly, there is already a lot that can be done. I mentioned an estimate of about 15% efficiency gains, which is possible to be achieved by using the current technology, but by just using the best cases available and also by changing the mindset, right? So we need such urgent action. And in terms of the business model, ideal business model, I heard from Jose that there are two critical ingredients. One is partnerships. It's actually bigger than that, a consortium of several players which would be solving the problems in different parts of the business. And secondly, energy, green energy. So yeah, so with that, I'd like to turn to the floor. Are there any questions? So yeah, please, Renate.
I have a question for Jeremy. Aside from very clean scrap or ore-based metallics, what else do you need in an EAF to produce automotive-grade steels? Or any high-grade steels?
Sorry, what else?
What else do you need for an EAF to do to produce high-grade automotive types of steels?
You need an educated workforce, and you need to have the right tools in place. No, people take this for granted, but I'm telling you right now, with all these EAF projects that have been announced, there's no way they're going to find people with experience to come and run those facilities to start them up. But we know that right now, even in North America, where we're already more than 70% EAF based, we have new projects going in, and they're having difficulty finding experienced people to work at them. So this is going to become a really critical situation. We haven't kept up with training and knowledge retention within the industry. It's something we need to address as soon as possible, because it also ties with all the things that we talked about so far today, is having a knowledgeable workforce. And again, it goes sort of with what Rutger is saying. You have existing technologies, people who understand them, people that know what they can do to push those technologies and what kind of flexibility is possible. So that's also part, and we need much, much more discussion. I get very frustrated that people, oh no, we already know exactly what we have to do to decarbonize. And I just look at that and I say, how could you possibly know what you need to do by 2050? There's no way you know right now. People ask me, what's the EAF going to look like at 2050? I said, I don't know, but it's not going to look like it does right now, because it's going to evolve. So, you know, you have to have a really open mind, not be too emotionally attached to things, and be willing to accept and listen to other people's ideas, because the more perspective you have, the better the solutions you produce. And when you only have one perspective, then you're either really lucky or really good if it succeeds. And if you're not, then we see the alternative.
Yeah, Philip, please.
Yes, sure, thank you. And by the way, great panel, very good information shared, and I appreciate the perspectives. And this question is more for Paul, but maybe Rutger as well. Understand the advantages of looking at existing technology and optimizing them. Paul, I agree that globally, scrap is not the immediate answer. Yet, it's kind of a follow the money situation. If you look at where the investments are being made, either through the growth of EAFs in North America or the blast furnace to EAF conversions in Europe, that's where all of the investment is right now. Some of these other investments are still playing catch up. So I guess, how would you respond to maybe when you want to look at existing technology, maybe that is EAF, because that seems to be the predominant way people are trying to decarbonize, at least as a first step?
Yeah, I don't know exactly if I can answer that, but I look at it, and it's already been said, there is only so much scrap in the world. We've taken it into account in terms of that forecast. So someone could invest in an arc furnace, they can use more scrap, but essentially that scrap is just going to come from somewhere else. So, and maybe Europe can do that, maybe North America can do that, start to use more scrap. but someone somewhere else is going to have to do something different. And so in my mind, it's a zero-sum game to do that. So there needs to be a focus on that something else, which is going to be hot metal-based. It's going to be ore-based in some way. There needs to be some focus on that to reduce the emissions there as much as possible. I'm not sure that answered your question, but...
I'd like to comment on that, because I believe that it's not about reaching the final goal and everything will be nice. It's actually abating the CO2 emissions or completely miss the target. It's actually a very, very hard world. And we might think that if we don't do what we can with what we have, we might totally miss the target and create a catastrophe. So therefore, there's no possibility that we can go around and be good people and no, I don't like CCS, and no, I wouldn't like any blast furnaces. We have to do what we can with what we have. And when I talked about competitiveness, I think that we have the people from looking if it's an economic problem or a financing problem. If you have fantastic projects, but probably not competitive, and you have these projects which actually produce something which is reasonably okay, and where the customers say it's okay, and that is definitely steel produced at a lower cost. I think that the people managing the pensioners' funds, they won't go for the nice, fine, very, very green thing, but not competitive. They actually say that, okay, we'll finance it as actually will stay alive for the 30 years that it has to stay alive for in order to be so it's not a very nice answer, it's not a very nice message, but it's the best message I can give.
May I add something as well,
Yeah,
Boris? Nowadays, because Paul, for example, I believe we have these general evaluations, and I appreciate that we do this diagnosis. But we, for example, gravity, we are committed to build, own, and operate a hydrogen-based DRI facility in France, 2 million tons, with a 2 billion euros investment. And I don't have hydrogen at 0.5 or 1 euros per kilo. So what is the magic? Back to the basics. This is basic business. Market is not all the same. You have a segmentation, and you need to address the specific needs of the different segments. So I can assure you that, for example, we are discussing much more than 2 million tons that we are going to produce with the customers in a specific segmentation that are willing to pay a premium that justifies the investment and the business model, the business case that we are developing. No, we will not resolve the whole decarbonisation challenge of the industry. But if we do 2 million tons of DRI in France, we should be able to abate up to 4 million tons of CO2, which is 5% of the whole French CO2 emissions. So my point, we have to look at the bottom up as well. Every initiative with a meaningful impact is something worthwhile pursuing.
Totally agree. Yes, Jeremy.
I think also several people have basically said this, but it's not a one-size-fits-all, and we should never expect it to be one-size-fits-all. We have different conditions in different countries, different resources available. So you can't just generically have a technology that instantly gives you decarbonization. So you have to dig into the process technology. You have to dig into the limitations. People talk about, oh, we're just going to put in EAF. How many people here know what the short circuit capacity is at the point of common coupling and why that's important? Anyone? Well, that's what determines how big a transformer you can put into a plant for an EAF. And you wouldn't believe how many people I have coming to me, oh, we want to put this 300 MVA transformer in and have a 300 metric ton furnace? And I said, well, what's the short circuit capacity? Oh, it's this. Well, that'll only support 140 MVA. So people don't recognize some of these technical aspects that you have to understand in order to make good decisions. And okay, I don't expect people who aren't directly involved in the steel industry to know that, but these are things that are real and have to be taken into account. And that's why one size doesn't fit all, ever.
Exactly. So, yeah, please.
I had a question for Mr. Vora from Mackenzie. You were talking also about CBAM, and you mentioned the impact. Could you maybe reiterate it a bit, and could you also say something if there will be only an impact on a specific part from the steel industry that is exported towards the European Union, or will that impact also be broader outside Europe, or only limited to the part that is exported? Thank you.
Yeah. So if you look at EU CBAM, the way they are going to kind of bring the steel industry into the purview of CBAM is gradually, right? So 2026, when they begin, it's just going to be 2.5% of the overall carbon emissions that happen in the sourcing country. But what's going to happen by 2034, they're going to have almost 100% of emissions that is happening in the source country. It's going to be taxed at the carbon price rate. Kind of trying to bring a level playing field for a lot of European manufacturers, because end of the day, Europe sits on the right side of the cost curve, as we call it. So it's a high cost producing hub. Now EU CBAM will definitely have their own implications. First implication that I discussed was that there will be an impact to Finnish steel trade, because that's going to make exporters in India, in China, they're going to make them 30 to 40% more expensive, bring them almost up to the level playing field. And currently, these exporters are exporting to EU because they are playing on the price, right? So they're going to kind of try to level the playing field. But EU CBAM has an impact only on the EU for now. It has some indirect impact to, about 30 million tons of steel being exported out of China. So, okay, that gets impacted. 15 odd million tons of steel being exported from India, yes, it gets impacted. These are small numbers, but vis-a-vis to that, if you look at the overall scheme of things, there will be other, similar kind of policies which we envisage gradually comes in. It's not that with EU and North America just having those kind of policies, but you might see in the medium term, countries like for sure like Japan, South Korea, China will also come up with those kind of policies where they're going to have their own carbon pricing mechanism, and they're also going to have some mechanism in which they will tax the importing players as well. Now, from a more wholesome perspective, yes, what we believe is that the Finnish steel trade will overall get impacted because production of steel will get more concentrated and localized because of these kind of policies which are coming in. And along with that, there are cost benefits which I mentioned, that if you are able to manufacture a greener metallic in a region like Middle East, in a region like Australia, and you are able to provide that to the suppliers, to the steel makers in Europe or in Japan or in China, at even if 5% or 10% cost benefit, at the end of the day, you are still claiming the same price when you are selling locally into your market. So that 5% or 10% goes directly to your bottom line. And, even a 1 percentage point to my bottom line, I would give my arm for that. So that's really going to be a major impact there.
Well, actually, we ran out of time, but maybe one last question, please.
Okay. My name is Sabina Grund, and I represent the global zinc industry. I'm with the International Zinc Association. Jeremy, thank you very much for that presentation and for broadening our view. You said primary metal, primary iron is used to dilute the copper content in the electric arc furnace. Now, when I look at the scrap that is fed to the electric arc furnace, a lot of it is galvanized with zinc. And that's a good thing because it makes the steel more durable, which is a sustainable use of steel. So I can assure you that the zinc industry wants the zinc back from this major use of its metal. And it comes back via the electric arc furnace dust. So if you dilute the copper content in the scrap with primary metal, do you dilute the zinc concentration in the dust as well? And if you do so, then you lose us as your facility to treat your hazardous waste.
No, so if you're, the amount of zinc that you have in your EAF dust at the baghouse is going to be based on the percentage of prime scrap that you're using that's galvanized. And almost all of it reports to the baghouse. It reports there as a combination of zinc oxide and zinc ferrite. Zinc oxide is very easy to recover. Zinc ferrite, not so much. Typically, zinc ferrite, you have to use a pyro process to break it down. So it is complicated. I worked for several years on zinc recovery processes for EAF dust. And so I'm quite familiar with that. But using an ore-based metallic, in the sense that it might displace the use of some galvanized scrap, but typically, if busheling is available close to the steel plant, then they're going to buy that first and use that to lower the copper levels, because that's going to be anywhere from a 0.03 to a 0.10 copper, depending on whether it comes from an integrated plant or from an EAF-based operation. And so it's already fairly low, and even if you're producing like an 08 copper spec, it's very close to what the spec, so it's neutral. Where we get into using things like shredded 0.16, we have to lower that to maybe 0.1, 0.08. So we typically have to offset that 1-to-1 with an ore-based metallic. So pig iron, granulated pig, DRI, HBI, okay, currently.
Yeah, I'd like to just comment on this dilution issue, because zinc is an excellent example where you can actually recover things. Most of the alloys, very valuable alloys that we have in steel, if they are in low concentrations, we actually lose them and they become tramp elements. So if you look into the future and you look at what decarbonization, and something we haven't covered here, is that in the future we need to have a much better recycling process in order to recover nickel, molybdenum, and the elements that you mentioned, and that we now dilute in order to make them less harmful. So what we have to do is actually have complex products, and this is a matter for the companies designing products. So when we produce complex products, we should label them, as you said, and say that this should be recycled according to system B. This should be recovered according to system C. And then you must have a system gathering this product, send them to recyclers that can actually upgrade them, separate the different alloys, and then send these alloys, these lots, to steel companies that they can actually benefit from scrap with a low chromium, 1, 2, 3, 4% chromium, 1, 2, 3, 4% nickel, and use it so that the alloys don't become tramp elements. This demands actually, because the alloy value doesn't cover these costs. So this demands actually having some sort of producer responsibility, like we have for cars and electrical appliances, covering this extra upgrading cost. And for the steel makers, it's going to be even more hard, because they will have to accept to get small lots of scrap. a steelmaker wants to buy 300 tons, 500 tons, 1,000 tons of a specific sort. And in this case, they will end up with lorries with 30 tons of a nickel alloyed scrap with approximately this amount of nickel. But if we really want to claim that we have 100% recyclability in the future, and where we don't lose the alloys, we actually have to start working with this. And most alloys have a carbon footprint much higher than iron. So just diluting it and letting these alloys become substitutes for iron or even impurities is not sustainable. Do you agree?
Yeah, but this is what is currently already done in the stainless industry, and with a certain grades of special steels, the kinds of things for aerospace where you produce steel and then you go into vacuum arc remelting or electroslag remelting, that kind of thing. I know why Rutger's bringing this up, because in Sweden they have a lot of these kinds of scrap because they have a lot of tool steel makers and special steel makers, which I'm very familiar with there. So yes, obviously that's, and again, this factors into the whole, how do you make the best use of the materials that you have? Now, there's obviously a cost to segregating, but in the stainless industry, they find it very cost effective to work this way. Okay, so, and that's not something which so far has transitioned into the more sort of general carbon steelmaking world. But again, you have to have an open mind, right? And you have to look for ways to be more efficient.
Okay, well, I think we are like 10 minutes above our time. Actually, we had a second round of discussion in mind where we wanted to discuss the decarbonization initiatives we see on the ground at the moment and what we might expect to see in the rest of the decade, how the decarbonization process could evolve in the rest of the decade, and if we should expect raw materials or energy emerge as bottlenecks already in this decade. But I think we should postpone this discussion to the Open Forum next year.
Everyone could just come 15 minutes early tomorrow morning.
Agreed.
It's not a problem. No? Come on.
So I think I'd like to invite Osa now for concluding remarks of the day, and maybe one internal, well, please join me. And maybe one final internal note for World Steel staff. Maybe for the next Open Forum, we should consider a session on mindset, how to accelerate the mindset change. Yeah. Thank you.
Okay, well, I think this is an evidence, again, of the interesting discussions on the topics. And I have a suggestion for your continued discussion. After the dinner, there will be an hour of open bar in the session between 10 and 11 tonight, and that's an excellent place to discuss these things. So thank you all very, very much for today, for everything, to all the speakers, panelists, to all of you who have been asking questions and engaging with everyone. We've now reached the end of the day, but the day isn't over, or rather there is an evening as well, and we are very happy to invite you to our gala dinner tonight. It will take place in the Antwerp Zoo. The zoo is basically just across the big square next to the train station, so it's a very short walk from here. We are going to start there for those who want to join us with a small guided walking tour of the zoo, around half an hour or so. It will go in groups, so not everyone at the same time, but we will start with those from about 6:15. From about 6:30, there will also be drinks and sort of a welcome reception. So those who go first to the walking tour can then come back and have a drink, and others can start with a drink and then have a walking tour. We'll start our formal dinner at 8 o'clock. So if you want to join the walking tour, please be there around 6:15, 6:30. And then for tomorrow, we are starting again in this room at 9 o'clock, and it's a full day again, 9 to 5 tomorrow. So thanks, everyone, and see you at dinner.